Imagine this, a single photon, a tiny particle of light. But its wavelength isn't just large, it's larger than the entire solar system. Could we ever detect it with any device we could build? Or would it remain completely invisible to us forever? In this video, we'll dive deep into the world of quantum physics and see why this isn't just an engineering challenge, but also reveals the limits of our understanding of the universe itself.
A photon is the smallest unit of energy in light or any electromagnetic wave. It has strange dual properties. Sometimes it acts like a wave, sometimes like a particle. The wavelength is the distance between two peaks of the wave. The longer the wavelength, the lower the energy. We calculate energy with this equation. E equals hc divided by lambda. So, if the wavelength becomes extremely large, the energy becomes unbelievably small.
The solar system is about 10 trillion meters across. Let's calculate the energy of a photon with a wavelength that size. E approximately equals 10 to the negative 20th electron volts. That's an unimaginably small number. For comparison, photons of visible sunlight carry about 2 electron volts, and photons from the cosmic microwave background carry around 0.0002 electron volts. We're talking about photons billions of times weaker than anything we've ever observed.
To detect a wave, your detector's size has to roughly match the wavelength. Cameras capture visible light photons with wavelengths of just a few hundred nanometers. Radio telescopes like Arecibo are 305 meters across, and FAST is 500 meters. But even the largest antennas on Earth don't come close to the scale of a photon with a wavelength the size of the solar system.
First problem, size. We'd need an antenna bigger than the solar system. Second problem, noise. The photon's energy is so small that even the thermal motion of a single atom would drown it out. Third problem, wave-like nature. At these wavelengths, photons stop behaving like individual particles and start looking more like a static, extended electromagnetic field spread throughout space. The longest radio waves we know of are just a few kilometers long. Gravitational waves detected by LIGO have wavelengths thousands of kilometers long, and that was already a monumental achievement. But photons with wavelengths the size of the solar system, that's far beyond anything current technology can handle.
This phenomenon shows us that quantum physics isn't always separate from classical physics. At these scales, photons become a large-scale field phenomenon, more like a standing wave filling the universe. It's a perfect example of how quantum mechanics and classical physics are deeply connected.
So are these photons around us right now completely undetectable? Absolutely. But for now, humans simply don't have the tools to even come close to measuring them. It's a humbling reminder of how vast and complex the universe really is. If you enjoyed this video, give it a like, subscribe, and share it with your friends. Stay tuned for future videos as we dive even deeper into the mysteries of physics and the cosmos.